All right. Hey, and welcome to the first lecture in the lecture series on the future of AI, self-supervised learning and foundation models. So there's been a lot of breakthroughs in AI for the last 1 to 2 years. Most recently, there's been a lot of buzz around ChatGPT, but it's only the tip of the iceberg. And in this course, I really want to teach you about the fundamental revolution that's occurring within AI right now, and how you can take advantage of that, whatever your background might be. So we've seen a lot of progress, and we have now text-to-image or even text-to-video models. We have superhuman robotics, self-driving cars, and we can now accurately predict protein structure from DNA sequences. And you might be surprised to learn that even in these wide array of applications, the underlying technology is still self-supervised learning and foundation models. We'll cover a lot. We'll cover ChatGPT, as I said, and for those who don't know, it's a very sophisticated chatbot that has a very human-like mastery of language and knows a lot of knowledge about the world that can solve tasks for you. We will also cover these text-to-image models like Dall-E or Stable-Diffusion, which can generate art from text prompts, and it's incredibly useful. In fact, basically all the images that you see in this lecture series was created by an AI. Maybe that's the first time in history. So AI has been talked about and hyped for quite some time now, but I will convince you that now is the time that hype actually becomes reality. So a little bit about myself. I'm Rickard, or Richard. I was born in Sweden, the land of ABBA and IKEA. I left Sweden when I was 18 years old to go to college, where I did my bachelor in mathematics at Stanford, and also a master in computer science at Stanford. Then took some time off and started a company that does self-supervised learning and foundation models for businesses. So I also hope to bring in a lot of industry and business perspectives. For the last 3 years, I'm a PhD here at MIT, where I do research on these topics. All right, so what will we cover? Well, in this lecture series, we will cover all the buzzwords. So we have neural network, supervised learning, representation unsupervised learning, reinforcement learning, generative AI, self-supervised learning, and we'll try to put it all together with a lot of examples and applications. In this lecture, however, we will focus on these concepts, and I really think those are the core ones, and everything else is basically a combination thereof. More specifically, today we will cover we'll try to provide today a short and succinct answer to what is self-supervised learning and foundation models. Then we'll go a little bit on a digression and a historical and philosophical journey and ask, how is the world structured? Because that will inform us how we learn in the world. Then we'll go through some application at the end. Right? And we'll try to cover this using intuition and a lot of examples. And I'll try to cover this in a kind of a simple but still deep way. Because I really think that if you're not able to explain something in a simple way, you're really not explaining it well. So that's what we're going to try to do. And we'll try to use science as well as business to convey this. So basically, you will understand why the hype is real. So let's get started. Since we're human beings, I think we cannot help but to use ourselves as a reference frame. And this is a very important question within AI, which is basically that at some point you're born, you're basically this blank slate baby, no understanding of how the world works, and you're fairly useless. But then as you grow up and you become an adult, you learn about how the world works, you can navigate it, you can create value and be very useful. So what happens in between, right? What happens in between you being this blank slate baby and to you being a useful, knowledgeable adult? So when we ask ourselves these questions, let's consider some alternatives about who or what might be responsible in imparting most of the knowledge that you have, right? who's most responsible for shaping and giving you the knowledge that you have about the world? Well, the first candidate we can consider is our parents, right? They raise us, they give birth to us, so they might be important in shaping and giving a lot of knowledge about the world. Secondly, we can think about DNA and genetics. DNA definitely gives us a lot of physical attributes, but also a lot of personal characteristics, right? But maybe it's more on a generational scale, and there's kind of, a delayed feedback loop, and it's very hard to affect it too much. And also there's a lot of flexibility. Identical twins can become very different based on where they grow up, right? Then we also have schools and academia. When we think about learning in general, that typically has strong connotations to schools, teachers, and academia. So maybe that's also a good candidate. Lastly, we will consider basically our more immediate environment and how our emotions and goals interact with that environment, right? You might want to be appreciated and have some kind of status in among your peers, or and that might, as you try to accomplish these goals of being appreciated and having some kind of status, you will learn how to, you learn how different things work when you interact with your environment and your peers. All right, so we can try to divide this a little bit further. So this nuance of learning from a parent, or there being this kind of parent-child or teacher-student or expert and beginner relationship, that's supervised learning. We learn from labels and a lot of input, and we learn from some kind of expert that does a lot of work to put the information in the right format for us. On the other hand, we have these delayed processes, where we have some kind of delayed feedback and we navigate some environment and trying to optimize some kind of end goal or objectives. And as we do that, we learn about the environment that we're interacting with, trying to optimize these goals, feelings, and desires. So this is reinforcement learning, right? And both of these approaches has been very well studied and within AI. For supervised learning, we've been doing it for a long time, and I think because most of the early researchers within AI, right, were professors, they're both typically teachers as well as parents. I think there might have been some bias there, and we really thought this is the way forward. And reinforcement learning has also been well studied. But it turns out that these by themselves actually don't work that well. And none of them are responsible for giving you most of the knowledge that you have about the world. Actually, you can thank yourself for that, because most things you learn by yourself. So how is this possible, right? Let's take the example of learning what a dog is. You don't learn what a dog is from your parent pointing it out or from your emotions guiding you. You learn what a dog is by defining the meaning of a dog by the company it keeps, right? We learn what a dog is by correlating and contrasting dog with other concepts, by observing dogs in different contexts. So you learn what a dog is by saying that dog is something that's walked by an owner with a leash. Dog is something that might have an antagonistic relationship with cats. It's something that chases frisbees when they're thrown, right? This is what allows you to understand what a dog is. And what you get by this process is a very relational understanding of meaning. And we don't get isolated and abstract concepts, we get very relational concepts. And as we learn about what a dog is by correlating and contrasting it with other concepts, like the cat, for example, right? In turn, we also learn about the cat as we contrast the cat with other concepts and phenomena as we observe cats. So it's a very, very powerful perspective. So when a child or a baby is pointing to a dog and asks its parents, like, hey, what's that? All the parent might be doing is just providing a name to something the kid or baby already understands. Just that it has the ability to use that information that it gets about the name and generalize that information to all dogs shows that it has a very robust understanding of what a dog is already. And it turns out that even things like language can be picked up in this way because dog is named or uttered more in context where dogs appear. So it's very, very, very powerful. So let's think about this a little bit more carefully as well. Let's say we want to understand and define what a mouse is, right? There's a very strong relationship between a cat and a mouse, intuitively for us, because a cat might play or chase a mouse. So we can understand mouse in relation to a cat. It helps us understand, right? It's part of this relational understanding that we have contextually. But what about the relationship between a mouse and a dog, right? It seems perhaps immediately less clear to us. It's a much weaker relationship. So let's use this kind of intuition that we have that there is a weaker relationship between a dog and a mouse than there is between a cat and a mouse. Because I generate all these images again using a AI that's trained using self-supervised learning, so has a very contextual understanding of meaning. So let's ask this AI to generate an image based on the prompt, a cat playing with a mouse, right? Here we generate something very sensible, and it all makes sense, right? And it knows how to interpret the mouse. It's a living mouse, right? But if we ask the AI instead to generate a dog playing with a mouse, it gets confused. It doesn't know how to interpret this mouse, and it generates a computer mouse. So it shows that it has the same very contextual understanding of meaning, and when that context is not clear, meaning is not clear. And I think, right, this is exactly also how we work, because you might not even be conscious about it, but when I said cat and mouse, you immediately thought about a living mouse, right? You probably didn't even consider that a mouse appears in other contexts, like a computer mouse, right? That's how quickly you collapse to like one interpretation space where the mouse was living because you had a cat in the same context. Because mouse is defined in its relation to cats. All right. So since we get this relational understanding by concept from observing them, the more relations that we're able to learn and pick up this way, the better understanding we get of each individual concept, right? It's this synergetic reinforcing procedure, right? This network effect here. Understanding something like love helps you understand what a dog is, because a dog loves its owner, right? So why not just try to push as many relations into one single model as possible? Train it on as much data as you can, with as many parameters as you can, to just get a better and better model with all of these synergy effects, right? And then use that as the backbone in a wide array of applications. So that's exactly what a foundation model is. And so it's the output of the self-supervised learning process. Big model, a lot of parameters, train a lot of data to have a lot of relations, understanding of a lot of relations. And then, of course, the prime example of a foundation model is your brain. That's exactly what we're striving for. And now, because of the success of all these, self-supervised foundation models, we feel that we're on the path towards artificial general intelligence, right? AGI, because this is somehow the missing piece that's so useful everywhere within AI right now, and it's feeding all of these new revolutionary breakthroughs. All right. So this might seem fairly straightforward. We can learn from observing things, right? We can learn from observation by defining meaning, by the company it keeps, contrasting, etc. So, and it is quite simple. So why did it take us such a long time to get here? This is where I think it's useful to go on a more historical and philosophical journey, and a little bit of my interpretation of this. So I think that there is two major concepts that's useful to kind of consider when we think about how the world is structured, how processes work here. And I'll try to define this using some examples. So this is, for example, designing versus learning, where designing is this clear, understandable process where there's a final blueprint in mind. And things are predictable, right, and work and interdependent, like a clockwork or software that's beautifully been designed with math and clarity, and everything works beautifully together, right? In contrast, on the other hand, we have learning, which is this unclear process. We might not even be conscious about what we're learning or how we're learning it. We just get better at something as we're exposed to it. There's no plan or blueprint in mind. We don't know where we're going to end up. We just see that we're getting better and better. And it's a very kind of adaptive and flexible and intuitive process. Similarly, we have order versus chaos, where order exists on the scale of planets and maybe on the scale of atoms, where things behave in these beautiful, according to beautiful equations like math and physics, and things are predictable and orderly. In contrast, though, we have more of our human world that's chaotic, where things are unpredictable, and we have weather and other human beings and animals, and they behave in fairly unpredictable ways, and it's hard to know how to summarize those into simple rules. And that's one of the core questions. Does there actually exist simple laws and equations that explains all the chaos that we see in our world, right? If we just think hard enough, can we find those beautiful simple equations that allows us to summarize everything that we're experiencing, so we don't need to take all that chaos into consideration. We just need to find these beautiful equations, right? That's a very important question here, what we should kind of focus on. Similarly, we have top-down versus bottom-up, where top-down basically is this, king or godly creature on top that has a very good understanding of the whole system, and of the bottom in some sense, like us human beings, without being really part of it, right? So in a top-down organization, the boss at the top can think about something carefully and come up with a plan, and then push that plan and decision down in the organization without having to start and take all those messy things at the bottom and close to the product or the customers, like without taking all of that into consideration. They can sit there at the top and just make decisions by being smart and careful. But in a bottom-up organization, right, we really need and really want to take all these details and messy interaction between customers and products, right, into consideration. And that has a lot of wisdom that should inform us of how we should run our organization and what decisions we should make, right? And it's impossible to get at that wisdom without being exposed and really immerse yourself into all these chaotic details in some sense. And I think that, at least in the Western world, we've had a very designing, order and top-down perspective for a long time. And I think we can trace this back to the ancient Greeks. So, for example, Socrates and Plato had this allegory of the cave, where they literally thought that there exists this perfect or godly world where it's sunny and clear, where concepts exist in their real pure form. And then you have our human world that we experience that's kind of very imperfect. And we're very corrupted by our senses, so we don't see the clear picture, right? They literally thought here, or said that, what we see is not the clear, beautiful concept that exists in this clear world. We see gods, walking with figures of those, and we don't even see the figures. We see the reflection on the stone wall, due to the fire of those figures. That's how imperfect our senses are, and how careful we should be to believe what we're seeing, and how much we should strive to understand the beautiful real world that exists in this abstract place. So for Socrates and Plato, there exists a pure form of a dog, right? A single pure example of the perfect dog, and all the variations that we're seeing in our world, in our human imperfect world, are just due to our kind of unimportant imperfect senses. And they truly strive to understand this pure world. And I think this makes sense because the Greeks were discovering mathematics, and they saw that, a circle, for example, a perfect circle exists in this mathematical world and obeys simple, beautiful equations. But every time you try to recreate a circle in the physical world, right, it's always imperfect. So this somehow, led them to believe that this real world is the mathematical one, because here things are beautiful and simple, and somehow lends to generalizations that can be useful. And of course, this has been extremely fruitful and led to a golden era of design that we've been experiencing, right? Where we have modern math and physics. We had the Industrial Revolution with cars and trains, etc., right? And we had modern medicine, and we went to the moon with this design top-down order way of thinking. So that's also perhaps why it's been hard to give up. But if, right, order top-down design is the be-all and end-all of our experience in our world, right? If we can find simple, beautiful equations that explain everything, and we don't have to deal with the chaos, right? If there is no limit to what order can explain, how come we're not better at finding that order, right? And if math is the process of finding that order, how come we're not better at math, for example, right? Why are we not more like computers or calculators? We've had billions of years of evolution on this planet. How come we're not adapted in a better way? And I think this is kind of a core clue, because if there is a limit to the chaos, right? If we live actually in a bottom-up world of chaos, finding order through math, etc., is not very useful. Instead, what is useful is intuition, flexibility, speed, all those things that we actually are good at. And I think this also tells us we're good at it because there is no simple order. There are no beautiful equations to find that explains everything that we're seeing. We have to face this chaos and try to contain it. So I really, let's say now that we agree with this and we think that there is a limit to the order. The world is chaotic, right? We have to strive to contain it and navigate and learn things in a world that is chaotic. We cannot just find beautiful equations and simple laws or rules. What can we do, right? Should we just give up? Or perhaps, is there some instrument that can help us out? We've had billions of years of evolution. What did we create? What we did create was the brain. And the brain is the best instrument that we know to contain, learn, navigate in this chaos. And then the neural network is simply just our best attempt at replicating the brain inside of a computer. It's flexible and adaptive. It has a lot of neurons or parameters arranged in this hierarchical way. And they do very, very simple computation on these neurons and parameters, but in this hierarchical way to kind of learn hierarchical features. And also they're very flexible, right? As you expose this neural network, and they can learn from a lot of different tasks. They're pretty slow to learn, but when they've learned something, they're extremely fast to execute. And you might say that there is some mathematics in how we define a neural network, but it's very, very simple math, right? It's just that we arrange this in composition after each other, and it allows us to learn very kind of complicated relations. But it doesn't help us to learn, it's not good at learning mathematics, it's very good at learning intuition, quick, fast decision making in uncertain environments. So great, right? We've now accepted that the world and concluded the world is chaotic, right? We have to deal with that. There's a limit to the order, and we now have a perfect instrument inside of a computer to contain that and learn from that chaos, right? But that brain is still inside of a computer. So we have to write software or mathematics to explain how the computer should navigate or what it should do in the chaotic world to learn from it, right? We need to give objectives and goals to the computer so it will do something, learn something, or be useful to us, right? So somehow we still need to go through this world of order to program the computer to use the brain in a way that's useful and to learn, right? So we still have to think about how we can communicate and give some simple tasks to the computer so it can start learning something by interacting with this chaotic world. So this is where we'll consider some alternatives of how we can try to, in an orderly fashion, present the chaotic world to the computer. So the first thing we can say is that, well, as human beings, we understand the world. We know how things work and how things are structured. Why don't we just try to feed that into a computer in a simple way, right? Let's structure the world, isolate things, label them, give names to them, and just give a lot of examples to the computer so it can learn about the things that we know, right? And this, of course, is supervised learning. But of course, it's very work intensive because you have to have these experts or human beings need to label things and show a lot of examples and isolate them. And also, can everything be labeled? Right? Something like love, for example, we might have a very intuitive understanding of, but how do you label love? And so it seems like a reasonable idea to try, but it has big drawbacks. So it scales with labels and human experts. And the question is, can everything even be labeled? And because of this, it doesn't generalize that well. So, for example, take this example of a dog or a cat. Right? It turns out that most things, things aren't really that categorical. There's typically a fairly continuous separation between concepts, right? If you have a dog and you go towards examples towards a wolf, when is the exact divide, right? There might not even be an exact divide. And right, as it sees more and more examples in the real world, it might get confused, right? Is this a dog or a cat? And this is a kind of a cat-looking dog, right? So it might start making errors. And so in some sense, it's kind of overfitting to the limited number of labels that it was given as it was training. And it's not able to refine itself as it sees new examples. So it's only really in the space of like unlimited amount of labels that actually starts learning robust understanding of how the world is structured. And that, of course, is intractable because it's too expensive. But it's also why you had these huge outsourced labeling centers where people spent all days, and they still do, just labeling things for a computer to learn from. But right, in the end, it doesn't work. So, okay, we tried this. We tried to structure the world, label it, make it simple for the computer to learn from, but it didn't end up working well. So let's now perhaps say that we go the opposite way. Let's try to encode as little information as possible to the computer. Let's just, now we say that as human beings, we have goals, we have desires and objectives. Because of that, we interact with the world trying to optimize those, and we learn about our environment and our world in the process. So why not just encode the computer and program it with desired goals and objectives, and then let it go out in an environment, optimize those by itself, and then hopefully it will learn how things relate in order to survive and prosper. So this, of course, is reinforcement learning. But I think it's very hard to understand even that, let's say, right, that you are this robot or blank slate, basically. You have no understanding of how the world works and is structured, and you're supposed to optimize these desires, feelings, and goals. So, where do you even start interacting with things, right? Like, how do you even start exploring your environment when you have no understanding whatsoever about how the world is structured, right? Like, basically, the state space of possible options is just super, super big, and you don't even know where to start. Maybe you want to become less hungry, for example, right? It's a pretty, there's perhaps still like a delayed feedback, right? If you eat something, you won't be full immediately, but it's pretty fast still with comparison to other things we optimize, like happiness, where there might be a long, years before something that we work towards makes us happy, right? But let's say you want to become full, right? Less hungry, and you're a blank slate, right? You would start, you don't have any idea where to start, so maybe you just pick something at random and you start exploring how the moon affects your ability to become full, right? You'll waste so much time trying to understand if the moon makes you full, and it takes a few hours before you understand if it actually works or not, right? And it's just infinite number of things you can consider, and there will be infinite number of hours before you even make any progress whatsoever. And more specifically, if you consider teaching a car to drive from a parking lot to a house, let's say it's a blank slate, it also just randomly starts exploring how the moon affects the ability to reach home, right? And explore something that's completely relevant. But let's say just by kind of coincidence, it starts exploring something that's actually useful, like other human beings. And, that's great, right? Explore something that's actually relevant and affects traffic, and it's important. But it's also very dangerous, right? Because it has no idea at all how human beings work or behave, and we can't really afford to hit like 1 million human beings before we make any understanding or progress whatsoever, right? Because we only know when we actually reach home. That's when we get positive, negative feedback, right? Did we make it or not? And we don't afford to hit 1 million human beings or crash 1 million times before we actually get any feedback. This is not good behavior in reaching home. So it's very, very expensive in this way. And we really need a guided exploration process, right? And some knowledge about the world in order to not die in the process, right? Or ways to be too expensive or risky and actually make any progress whatsoever, right? We need some basic understanding of how the world works. Consider putting a baby in the seat of a car, right? A blank slate. How many millions or billions of years do you think it would take for this baby to actually reach home, right? And then it would get a candy or something, right? Like, it would take billions of years, and if it did reach home by just sheer coincidence, it would have to be able to use that information and feedback to make it again, right? So that's how incredibly hard it is. Like, some of these things might work better in chess, where there's like simple rule and the state space is so much smaller, but in the real world it blows up immediately. So it's completely impossible, right? So what we do need is a basic but broad model of how the world works, achieved by just observing the world, right? Because the only thing we can really afford. So this is where self-supervised learning comes to rescue as the only real viable options, right? Where we can learn from observing the world by defining meaning by the company it keeps, by all these contrasting correlations, and gives us a robust model of how the world is structured and works. So to recap, we went on this journey philosophically and historically and said that the world is actually chaotic. There's a limit to order, and we have to accept that the world is chaotic, and we need to be able to contain that in some sense. And the brain is the best instrument that we know of to contain this and learn and navigate this chaos. And a neural network is a brain inside of a computer. Still, we have to communicate with this brain on the side of the computer using some structure or math or software. But supervised learning, right, scales with labels and human experts is too expensive, and it doesn't generalize well enough because it overfits and the world isn't categorical. It's much more continuous, much more gray scale than just black and white, right? And reinforcement learning, the possible options to explore is infinite. You will make no progress if you're a blank slate. It's too expensive and risky because you cannot, die basically before you make any progress, right? You need to have a basic model of how the world works, so you can know where to start and what's relevant. So that's why you need self-supervised learning, to learn by just observing the world, right? It's the only viable option, and then we can use this model and plug it into reinforcement learning as a good starting point that can help us out, and we can use it for a lot of different tasks, right? And we use the self-supervised learning model as well as a starting point to classify things, so or be able to say if something is a dog or a cat, right? So that's why self-supervised learning is so revolutionary, because it is the starting point and the model that everything else right now is built on top of. All right. So let's get a little bit more tangible and hands-on, and consider some more kind of detailed examples of how self-supervised learning and foundation models work. So there is a lot of different algorithms and techniques within self-supervised learning, and we'll cover all of these in subsequent lectures. In this lecture, however, I will just briefly comment on predicting the future and positive pairs. But the common denominator between all of these different approaches are, right, they learn only from the data itself. So no labels needed, right? They learn from just observing data, and they train these big models on a lot of data, because you don't need a human being in the loop, so you can just get as much data as you want, train on it, and then you have this huge model you can use in a lot of different tasks, basically. All right, so predicting the future approach. Let's see. So predicting the future approach rests on this assumption that in order to predict the future, we need to understand the past. This actually started off in language and text, where we would download just text from online, the internet, so we have unlimited amount of data. We just download text sequences, and we would remove the last word in a sequence and predict that word based on previous words, right? So let's say we train a model to do this, and if it's able to do this really, really well, right, optimally, what does it learn? And what is it able to understand from text itself just by learning to do this task? Does it need to understand grammar? Well, in order to generate the next word, it needs to understand grammar because it needs to generate sensible sentences, right? Does it understand the meaning of words? Well, if I tell it to generate the next word in the dog is, right, it needs to generate adjectives that describes a dog, so it needs to understand the meaning of words, right? And let's perhaps assume that text, right, that how text is written and how you write text depends on if you're happy or sad. Then it also needs to learn, based on text, if this person is happy or sad in order to be able to complete the next word optimally, right? So it needs to be able to infer that from text. If text changes based on political beliefs, it also needs to understand the political beliefs from text in order to do that optimally and use all the information available, right? I mean, it needs to understand it implicitly, indirectly, in order to solve this task. And it turns out that it actually does learn a lot of the different things, right? It's hidden from us, but we can decipher it afterwards. So it's extremely, powerful to the extent that it's almost scary, right? And also consider if we ask it to complete the next word in the sequence, what is the capital of Sweden, ? Right? The only sensible answer is Stockholm, the correct answer. So it also needs to solve tasks for us and to get an understanding of knowledge and the world. So it's extremely powerful. And this is the fundamental technique behind ChatGPT. And we'll go through that in detail later, but that's basically how it's trained. Right, and this of course also applies to our physical world, right? If we think about a time series or a series of events, basically frames, and if we train a model to be able to predict the next event based on previous events, it somehow needs to understand the concepts involved to do this well, right? Let's say the model is trained on this and it's now able to after seeing a owner walking a dog with a leash, and then in the next frame it sees a frisbee in the hand or something. If it can predict now that the owner will probably throw that frisbee and the dog will run to catch it, well, then it basically understands the concepts involved, right? It understands how a dog, a human being, and a frisbee relates to each other, which means that it understands the meaning of those concepts. So it's very, very powerful. We also have positive pairs. This is typically used in vision, where we download as many images as we want from the internet. And here we'll just say basically that we believe that concepts that appear in the same image are more related than concepts that appear in different images. So basically we'll define features around images by taking an image, we'll create two random crops, and we'll try to push the features of those two crops closer together because they're part of the same image. And then we'll push them further away from other images. So we somehow define similarity here by co-occurrence within an image, right? So basically, a person, people that share a lot of friends are probably similar people. This is kind of the underlying idea here. Like if you share the same company as some other phenomenon, you're probably similar. So even though, let's say that we have two different species of dog, even though they would never appear in the same image, as long as they appear with other concepts that they share, right? As long as both of them appears with frisbees, leashes, and owners, they will be mapped to a similar space, and they will be, somehow similar in meaning. And this is extremely, extremely powerful, and it's basically state of the art when it comes to understanding, visual concepts and images. All right, let's now consider two applications, one in science and one in business. So let's say we want to do some genomics. We want to predict protein structure from DNA sequences. So what we might do as intelligent human beings, we might say that we can spend 50 years of research, as we've done, right? We can map up, look at the genes and the genomes and say, well, what kind of sequences reappear frequently in the genome, right? That's genes, this unit of sequence that's kind of frequent. We can then go in and perhaps mess a little bit with the genes and different DNA and see what kind of effects it gets in mice or something, right? Do studies. We can look at evolutionary trees and think about some kind of relatedness and use that to define and create features for DNA. Or we can say that, well, this actually looks kind of like a language, right? We literally have letters here, this DNA base pair. And we also have unlimited amount of DNA data, basically. I mean, each one of us have an abundant amount of DNA, and it's fairly cheap to sequence. So data is no shortage. So what if we train a model, using self-supervised learning and just try to predict the next letter or DNA base pair based on previous letters or DNA base pairs, right? Let's say you train a model to do this on a lot of data with a lot of parameters, and it's able to do it really, really well. What does it learn? Does it learn what a gene is? Well, if it's inside a gene and it's trying to complete it by predicting the next DNA base pair or letter, of course it needs to understand what a gene is to do that successfully, right? It needs to say like, well, I'm inside a gene right now, and this is how it looks like. It also needs to understand, to do it successfully really well, how genes change, in relation to other parts of the genome, right? So basically, well, it needs to implicitly understand that it's trying to complete the gene or DNA inside of a dog versus a cat, right? So indirectly and implicitly in this process, it understands so much about genes. And if we force it to create features of the DNA while doing it, we can then use those features to correlate that with protein structure, right? After 50 years of the research that we've done on DNA, we still only understand a few percentages of the DNA. But this model can now, do this and understand much more than we have, been able to do this last 50 years. So it works extremely well, and it's a very, very powerful approach. All right, okay, let's go to business. And it's actually an example from my startup, where we worked with a grocery chain. So typically when you start working with a business like a grocery chain that wants to understand its customers and its products, they're very top-down perspective. And they might have management and consultants that try to think smartly about people in general and their customers, right? They might define these sensible, user profiles or groups like pet owners or families with kids, and then they might do a lot of different, user studies or ask a lot of questionnaires and try to, understand or ask different questions like, how old are you, what are your interests, and then hopefully understand how that correlates with purchasing habits, right? But of course, this is very work intensive to do this just by yourself, and it's a lot of wishful thinking that we're kind of smart enough to just figure out this by ourselves, and that we can even just ask people about themselves and their behavior, because first off, we don't know what questions to ask, right? It's very hard to know what characteristics determine somebody's purchasing habits, right? And probably don't even know it ourselves. We don't know what affects our own decisions, right? We're not conscious and about that and self-conscious enough. So that turns out not to work well. So you can take right, and also right, it's not enough to do 5 user profiles. Of course, every human being is unique, and to do well, you need to account for that. So we can take a different perspective and basically let the customers do the job for us. We can let the customers define meaning by interacting with products and defining context and relations that we can apply self-supervised learning to, right? So if we train a model to kind of decipher or learn these relationships or predict the behavior of the customers, it starts understanding all these different concepts, how products relate, and also a infinite amount of different user profiles, right? Based on behavior, right? It just learns, as I said about text, it just learns about who a customer is based on its behavior, and it can quickly adapt and give a better experience. And that also allows us to understand how products relate, because people treat vegan products in a similar way, so then we can understand what is a vegan product. But here, for example, right, if somebody might buy a wine and cheese and chocolate on a Friday night, it's probably some adult, and it will have to start learning that and pick it up in order to be able to predict as well, right? But if somebody buys soda and candy a Friday night and chocolate, right, it's probably a child. And then, if it starts to learn this and pick this up, and it then understands, for example, right, that this is a family with kids that's out shopping groceries, then it can recommend, both wine and cheese and chocolate as well as soda and candy, because this is a family and wine and cheese is the adult equivalent of soda and candy, right? So it needs to understand all this, and it does start to understand all of these different things, relations, but just training this on a lot of data. And because, right, behavioral data is very cheap to get because you just need to track people. It might be very expensive to get 10,000 questionnaires, and you think that's good data. It's fairly useless. But if you have 1 million customers, that visit you once a week as a grocery chain, if you track those a little bit, you can get to 1 billion data points after a few years. And that's really, useful data, and somehow actions don't lie, right? Behavioral data is extremely insightful. Okay, so to Right, but also I want to say that this model now, right, it starts to understand your products, your customers, and how they relate. And if you were in retail, that's your whole business. So now that you learned all these different concepts and relations, you can use it everywhere in your business, right? It's a very foundational model of your business that you can plug and play and use everywhere, and should really, drive a lot of the decision making. So it's extremely, extremely powerful and a new way of thinking of how to use AI and data within businesses. All right, so to summarize, we started off providing a short and succinct answer to what is self-supervised learning and foundation models. We then went on a more historical and philosophical journey and asked, how is the world structured? That told us that the world is chaotic, and we need to use a replication of the brain to contain that chaos, the neural network. And then when we wanted to still kind of interface with that brain inside of a computer, we said that the alternatives of supervised learning is too label intensive and doesn't generalize well, and that reinforcement learning is basically too expensive and you make no progress as a blank slate. So we need to have self-supervised learning as a way to just learn from observations to get a very broad foundational understanding of how the world works and concept, and then we can then use this basically everywhere, right? It's like a backbone of our understanding. And I want to leave you with this image, that meaning really is relational, right? And I want you to think about this yourself as you now, after this class, go around and view things. Do you perhaps have a self-supervised learning algorithm going inside of your own head? Like if I take this device and I would remove my hand, then it would keep floating. You probably will be surprised, maybe even upset. And you would start to understand what's going on, and you would try to understand what's going on right now, and you would try to correct your mental model of how the world works, because you were not able to predict this event based on the previous events that you've seen so far. Right? So we probably have this algorithm ourselves where we try to predict the next thing that's going to happen in our environment all the time, and that just allows us to organize and structure the world better and better, right? All right. So next time we will, as I said, go through all the different algorithms. It will be very useful, it will be more tangible, and should be a lot of fun. Yeah, feel free to check out our website, and I can take questions. Okay, so the question is, in the grocery examples, how do you view the data to be able to apply self-supervised learning? Yeah, so what we do is we just look at the behavior of customers, their interaction with the company, like purchases, search queries, marketing emails, etc. And that allows us to build an understanding of the customers and these events they interact with. And I think it's also worth pointing out that data is really key, and it feeds this whole self-supervised learning pipeline, right? Bad data give bad solutions, and we see more of this. And it's also why there's some kind of arms race about data protection, etc. Right? China has very relaxed rules, and they can build really, really powerful models because they can apply this way of learning from just a lot of data that they track, right? While in Europe we're more strict, for example, or America as well is more strict. And then it becomes an arm race because this data is so useful and powerful to build models and AI. All right, next question. Do we learn the categories while training, or we infer them afterwards? All right, that's a great question. So basically, we'll infer them afterwards. We don't want to mess with the model when it's learning, but it's basically like an employee. If you have an employee that's at a company or organization for a long time, it learns a lot of things, but you have to ask sensible and reasonable questions to this employee somehow to learn what it's learned, right? So we apply these algorithms, they learn something, then we try to ask the right questions, and we try perhaps to dissect the brain to understand what is learned, right? You can cluster embedding vectors or certain features around products, and you get one cluster that's vegan products, for example, right? This is how it works, and then you get clusters around other things. You might be surprised, like when we did this for groceries and clustered users, right? We had customers, we had some that were more explainable more immediately, like families with children, but we had one user group that was, strong cluster that was initially best defined by buying feta cheese, right? And then you had to look and understand more, like who is this user group that's growing and important for us? And it turned out that they was kind of hipsters, in the inner cities, like a growing demographic and customer base, but you will never get that from just a top-down perspective, right? But you got to see it from the data. Right, and also the question is, maybe questionnaires are not useful because the questions are biased and bad. I mean, completely, right? But what questions should you ask? And also, right, it's not only what questions should you ask, but also, right, how will you get truthful and informative answers? We're not very conscious about, how we actually work. We have a lot of wishful thinking, and we typically just do something and we rationalize it afterwards. So I think it's very, very hard. In some sense, actions don't lie. And that's key here as well. Will I talk about my topology paper? Well, I won't really. So I started off my career within applied topology. And topology is basically a study of shape and structure and connectivity. And I think the relationship between topology and self-supervised learning is fairly strong but abstract, right? If you want to think about relations and relational meaning in relations, that's kind of a graph and connectivity. So that's somehow how topology comes into the picture. And so it is quite interesting, but we won't very explicitly talk about that. How much do we interfere with the model to make it interpretable? Yeah, that's a good question. I think typically the sad thing is that every time we stupid human beings try to interfere with the model, we typically just make it worse. So I think it just empirically doesn't turn out to work out that well. But sometimes it helps if we encode like a stronger bias, right? If we have less data, etc. But if we have a lot of data, it's typically better to let the model just chug on and learn by itself. Okay, question is, what is my critique of interpretable machine learning? Yeah, I mean, I was in that field for a little bit, interpretive machine learning, which is basically how we try to understand what these models are learning, right? As human beings, we want to be able to understand what's going on, to trust it, and to use AI more broadly. And that is important. But I work with kind of a lot of seasoned professors, and I think there's this divide between kind of a younger generation and old generation, where a lot of times they would basically say like, well, I know we're using a new network here right now, but I promise you, like, it's not needed. When we just understand what's going on better, we can put a nice, beautiful equation there instead. And if you just understand carefully what's going on. But that's what I think I've kind of understood now, is that there is no equation to be found. That's the thing. That's why AI is so powerful, because we give up, that quest because it's not fruitful enough, right? It's like our brain. We cannot collapse our brain to just simple rules. We need all these different parameters and neurons. And I think that's somehow my critique of interpretable machine learning, is that not everything can be interpreted by human beings, sadly. Go back to slide. Okay, 1 second. Okay, so in this, so in this slide, we have generated image of text, and the question is, why is the AI not good at generating text? The text is nonsensical and not even looks, but it's not even real letters. That's a great question. And I think this is, also shows that this AI is definitely limited in its capabilities, right? It's not very intelligent because it cannot even handle something as simple as generating, real text. Of course, like, you can solve this. Google's version has solved this, but They kind of, went in, meddled with it, and helped the computer along. But also, yeah, I do think that that's just not just smart enough. And when it comes to kind of, multimodalities like images and text, I think that we're making progress, and the path forward is very clear right now, which is just more data and more compute. And that's and that will get us a long way, and it will, and it has, right? I think the big question is, where does it stop? At what point will we, have to think differently a little bit, because the current techniques and approach is not good enough to it will basically, the progress will slow down. So, we don't know what's going to happen, but I think when it happens, right, I think that's the thing. This won't get it by itself. It won't get us to human level intelligence, but this is the foundation that human level intelligence rests on, as well as for us as well. We use reinforcement learning and supervised learning and all these different things, but it's all built on this self-supervised learning model that understands the world, from just observing it. That's the core kind of component. But then we use a lot of different things and tricks to use that and to solve tasks using that understanding. Okay, related question: why is this self-supervised learning like ChatGPT not good at solving math and logical reasoning? Right, this is what this lecture has been about, that it's not good at math and logic, etc., because we're not, right? It's the same kind of approach. It's supposed to contain and learn from this chaos, be intuitive, flexible, and quick. Math is different in that sense, right? And the strength of neural networks and this way of learning is that, it learns things by relations, and it's flexible and can learn different things, but math is a very different, it's a fairly different process where it's, one thing that's very dependent on the previous step, like a multiple, chains of reasoning, and that's just hard, right? It's algorithmically hard. And your network might not be the best instrument for that, who knows, right? But it's still pretty good. And it definitely will get better as we get more and more data, right? Because I also want to say this, that, right, somehow when we ourselves, we're good at mathematics, not in spite of our, or despite of our intuition. We're good because of our intuition, right? Because it's all we have. If I worked with a lot of good mathematicians, like Fields medalists, etc., and they don't think about math just as cold machines. They think about life and death, and they involve all their emotions, intuition and visualization to do math, like an art form, right? So that's why, somehow, intuition, feelings, and visualization, and this is what we have to work with, and we need to involve all that to be good at something and solve something. Because if you try to do math just using pure logic, you're completely powerless. And I think it's quite interesting, because when I started off my career in AI, people said that the things that AI will never be able to solve is art, because it's so human. We said music and images and stuff, and art, but that's what we're seeing now. That's the first that AI is able to solve, because it's literally, good at those things that art comes from, this intuitive process, right? The emotions are involved in some sense. So I think that's very, very interesting.